Thanks for the introduction. Outdoor lighting is very interesting and important. Look at this beautiful image taken at sunrise in Quebec City. The golden color and the reflections are all created by the two main light sources, the sun and the sky. The key feature of outdoor lighting is its dynamic range, which is the ratio between the brightest and the darkest intensity in the context of light. In this outdoor panorama, the sun is hundreds of thousands times brighter than the shaded region. Of course, the projector doesn't allow me to show this, but if we re-expose the sky, we will see that even if we divide the sky by 10 to the power of 5, we can still see the sun. To capture such high dynamic range, we need some special equipment. We need to combine at least 7 LDR images at different exposures into a single HDR. Because even the high-end cameras don't shoot fast enough, so we need to insert a neutral density filter between the lens and the camera to capture the sun. This complicated capture procedure restricts us to use and understand outdoor lighting, because most of the time we deal with LDR images. Instead of capturing outdoor lighting, we propose to learn to predict the extremely HDR outdoor lighting from a single LDR panorama using convolutional neural network. Our key idea is to rely on a large data set of synthetic panoramas lit by real skies. Our basic assumption is that the sun is centered in the middle. This can be easily done by computing the largest saturated region in the sky. Our main contributions are that we are the first to frame LDR to HDR problem as a deep learning problem. After we submitted our work, there are at least 2 following papers working on LDR to HDR using deep neural networks. We also provide a novel real LDR HDR panorama dataset and introduce 3 novel applications. In order to train our network, we generate a large dataset of synthetic panoramas lit by real skies. Here are 3 examples from the Laval HDR sky database, which captures real HDR sky images over 3 years. Then we use those sky images to render a large city model. Finally, we got around 58,000 HDR panoramas. Then we generate LDR HDR pairs, then we can train our network. Our network contains 2 main parts, the encoder and the decoder. The encoder compresses the LDR image into a latent vector. The decoder directly generates the HDR. There are skip links between the encoder and the decoder. Here we use L1 norm to compare the images. The figure in the bottom shows the cumulative error. You can find more detail in our paper. The first column shows the error between the LDR and the HDR. The second column is our prediction. This is the big improvement, and we can make it better. We use a small branch to directly estimate the sun elevation from the latent vector. Here we use L2 norm to compare the sun elevations. Then we get a better performance by combining the sun elevation loss with the HDR loss. We also render a virtual object in the network. Here we use L2 norm to compare the rendered images. By combining the render loss with HDR loss, again we get a better performance. We observe that by combining 3 different loss functions, we can get the best performance. Here are some results on the synthetic dataset. The first column shows the ground truth HDR and its render. This render is a spiky sphere looking at top to bottom. We choose this theme because of its complicated shading and shadows. The second column shows the predicted HDR and its render. Our approach works very well on the synthetic dataset, but we are wondering how well does it work with real images. So we captured a novel real dataset. The LDR panorama is captured with a Recoil CTS camera. The HDR sky is captured with a Canon camera. Then we replace the sky in the LDR panorama with the HDR sky. Then we get the HDR panorama. We repeated this capture procedure 400 times over 13 days. Here are some results on the real data set. The first row shows the LDR result, and the second row is the baseline result, which is where we directly apply the model trained on the synthetic dataset to predict the HDR in the real dataset. This is a slight improvement in some aspects, but we want to make it better. We did more experiments in two scenarios. First, if we do not have the access to the camera. Second, if we have access to the camera. In the first case, if we do not have the access to the camera, we can augment the synthetic dataset by applying different camera response functions. We can also change the white balance. By augmenting the synthetic dataset, we get a better performance. In the case of we have access to the camera, we can calibrate the camera with this color checker. We get a better performance. We can also fine-tune the baseline model with a small amount of real HDR data. Then we can get the best performance. Here are some results on the real data set. This is the 25th error percentile on the fine-tuning model. The first row shows the ground truth HDR. The second row is the prediction. The image in the bottom is the rendered images. Then the 25th error percentile, 75th error percentile. We can see that our prediction is very close to the ground truth. We can apply our mesh into different applications. First, we can use it as a single-shot outdoor light probe. Imagine that if you want to get the outdoor lighting in this outdoor scene, you can just hold this point and shoot camera. With just one click, you can get the LDR panorama. If you directly use this LDR panorama to render, you will get this dull render result. But with the approach, we can get a much better render. Look at the hard shadows and the reflections. Notice that this result is from our fine-tuned model. We can also insert virtual object in front of the conference hall. Here the golden bun in front of the conference hall. Another viewpoint. Since I carried the CTS camera in a Wednesday breakup, so we can insert bunny in Venice City. Another place. One more. We can also make Google Street View Imagery HDR. Here is an example from the Google Street View. If we directly use it to render, we'll get this result. But with the approach, we can get a much better render. This result is from our domain adaptation model. You can find more detail in our paper, or we can talk in the poster session. Here are more results on the Google Street View. A quick conclusion. We propose to learn to predict the extreme HDR outdoor lighting from a single LDR panorama. Our main contributions are that we are the first to frame LDR to HDR problem as a deep learning problem. We provide a novel real data set and introduce several novel applications. Our code and data are available on our website. Thanks very much.
Are there any questions? Could we have the lights on in the main room? I have a quick question. So basically, as far as I understand, you're training your system by using the brightest spotlight as the source of light, but then you could apply it to images where there was no sunlight. So, like for example, the last images that you shot here. So has your system learned to estimate the shadow direction and the illumination direction from images? Have you looked into that?
I think the highlighting the lighting from both from the sky appearance and also from the hint from the ground, like the highlight from the ground and the shadow from the ground. So our network can hallucinate the saturated region in the sky. So did that answer your question?
Yes. I was wondering if you looked into, if it learned to detect that or to locate the sun from the shadows and shading.
Yeah, we can find the sun elevation from the panoramas. We have a branch can directly output the sun elevation in a panorama.
Okay. While I don't see any more questions, maybe we can go on. Let's thank our speaker.